Good morning. It is the physics video lecture, Physics 105B video lecture 18. We're starting a new topic, rigid body motion. And I mentioned last time we'll start with the motion around a fixed axis. And then it gets more complicated, but this is a good review, it's a good time to review material from Physics 4A. And get warmed up for the rest of the subject. So, motion of the rigid body and I will bring in some demonstrations next time too, maybe just to show some of these things. But we're talking about rolling objects, we're talking about the physical pendulum, one of those standard things. And the way we're going to build the theory allows us to do a little interesting mathematics of integration theory, finding some different centers of mass, moments of inertia, things like that. So I'll begin with the idea that we've been doing point systems. So systems of point masses, point systems, and here n is a considerable number, and what makes that into a point system, into a rigid body, is that the separation distances of all these point masses are fixed once and for all. So that's how this theory will fit into the general theory we've been doing. So we have conservation laws and things that we get to inherit, but the rigid body has fixed separation distances between the point masses. Fixed separation between point masses. That actually reminds me, taken from that point of view, the general mechanics of point systems, you can go to the rigid body, as we're discussing now, and all these relative distances, all these positions, these distances are locked in place. On the other hand, the body could be elastic, and then the separation distances are not fixed, but the displacements are very small, okay, in a point system. Then you could stretch, compress, and so forth. That would take us to elasticity theory. And of course, if the point masses can slide again with respect to each other, you can also make a transition to fluid dynamics as well. So continuum mechanics. But the way we're doing it, this rigid body, now all the point masses are locked in place, and therefore you can characterize the motion of the rigid body by just a couple of quantities. So motion characterized by the position of the center of mass location of the center of mass. And then there will only be a couple more quantities. Of course, that's a lot more than a single point mass has. And when we get into the general theory, we'll have two more vector quantities to characterize the rigid body. But for the moment, if we just have the position of the center of mass, we already learned that this, I'm just going to call this the example. Give this example before. If we've got the position of the center of mass, this body can be tumbling and doing all manner of complicated things when we throw it. But in the absence of air resistance, the center of mass will just describe the classic parabolic trajectory that the point mass describes. Okay? That's something we already learned when we did our conservation laws for a point system. And that, of course, holds true for the rigid body. But what we're going to do is get the center of mass position, and then we're going to talk about axis of rotation. Later on, when the axis is not fixed, things become a lot more complicated, but right now we're keeping it at the same level we had in Physics 4A. Okay. So we're going to talk about locating the center of mass, and then determining axis of rotation and the dynamics about an axis of rotation. So 3, and then I could say 4 here. We'll get to the dynamical equation. Good, so let's look at a couple of interesting center of mass problems. Good, are we numbering things? Yeah, center of mass. We have its definition that I'll go ahead and call it capital R for the moment. For a point system, sum of all mi ri, we've got these moments divided by the total mass. So that's for a point system, and for a continuous system, we replace this sum with an integral, or dm. In fact, we were looking at that the other day when we were doing our quadrupole expansion. So we'd have rdm over the integral dm, and this integral over the body, okay, right up there over the body. So let's do an example, or a few examples. An interesting example is if we have, say, a semicircular wire. So a semicircular linear mass distribution. Semicircle M R, mass M, radius R, and we want to locate the center of mass. Right, our intuition tells us it's going to be on the symmetry axis, and it's going to be somewhere here. Okay, so it's not actually going to be within the mass itself. Okay, which is this. This could be some version of a horseshoe. So how do we find that? We have by symmetry the R sub x. Bad choice of letters here, huh? Let's use this lowercase. R center of mass. R center of mass, okay. So what's in a letter? Center of mass. So x is going to be equal to 0. What we want is the y component of it. I'm going to change, okay. Center of mass, y component. Okay. So we need integral y dm over integral dm. Okay. So that's the vector sorting, that we just took the x component, symmetry clearly makes it vanish. Now we have the y component, y dm, and let's just continue this here. Of course, the denominator is just going to be the total mass. In the numerator, best thing we can do, the dm is going to be m over 2 pi radius. That's mass per unit length. And then we'll go ahead and use, for y, we'll use r sine of phi. Like that. And then for the dm, we have mass per, so we need an r d phi. Okay. So you'll see the construction here. We had the y, the dm is, I split it apart, maybe I should keep it together here. So you got m over 2 pi r d phi, and then we have r sine of phi. This is nice because you can see we could choose our boundaries of integration depending on what portion of the entire circle even that we had, or the semicircle. And in this case, we're going 0 to pi. And we'll work that out over here. So we have m 2 pi radius. We've got the r squareds coming out. And we're just left with d phi sine phi. And of course, we've got 1 over m over here. So the integral of d phi sine phi is negative cos phi, cosine phi from 0 to pi. So that's going to give us 2. Okay. Cosine of pi is negative 1, so it's positive 1 plus 1. So that's going to give us 2. Working back here, so we have m 2 pi r. We've got the m right there. We've got the r squared, and we've got 2. So when the dust settles, we would have r divided by pi. You know, I think I made a mistake here because that I'm not r over 3. Once more with feeling, we've got m over 2. Oh, there's a mistake. It was m over pi times r because I only had the semicircle. Okay. M over pi times r. So we end up with 2r over pi. Yeah, let's correct that. Okay. The mass per unit length over the semicircle. Okay. Good thing we got that. So there's our answer. Let's go ahead and write that down. Equals 2 over pi times r, so that's roughly 2/3. Makes more sense. So roughly 2/3 of the way up. And this is an illustration of what I just said about this point systems theorem that we had. So the center of mass of this object is what would, think it's a horseshoe for instance, you know, it would be tumbling around its center of mass. The center of mass would describe this parabolic trajectory, even though that's an empty point in space. Okay. Good, so we have that. I will do a related one, or I'll assign a related example for homework, namely the semicircular lamina. So this next example we will call homework. Find the center of mass of the semicircular lamina, which is just a flat semicircular object. Again, we'll go R here. We've got our X and Y axis. By symmetry, of course, it's going to be on the Y axis somewhere. And since it's a continuous distribution in the plane, we expect to get something different. So we can set it up. The center of mass of the Y coordinate, or the Y coordinate of the center of mass, would be 1 over the total mass. And now our dm would be 1/2 mass over, so it's mass per area. So it's mass pi r squared divided by 2. Okay, because that's half the area there. So there you go, you get a 2 right here. And then you need a D area. And you need Y as well. So what you're going to do on this one is use plane. Well, you can do it different ways as well. Maybe you can do it 2 different ways if you want. One way you can do it is with plane polar coordinates. Again, but this time use plane polar coordinates. But this time you're going to have to integrate your d phi from 0 to pi and your dr from 0 to r. Okay. So it's going to be a little different, slightly different result. Should be good. Okay. So there's that center of mass. And in doing these integrals, the convenient coordinate system is very important. So here was clearly plane polar coordinates, likewise up there. This next example, let's take we're on this circular theme. Let's look for the center of mass of the hemisphere. So the center of mass of the hemisphere, now we have X, Y, and Z, and we have this hemisphere right there. And you know, the center of mass is going to be located somewhere there on the Z axis. So again, X center of mass equals 0, Y center of mass equals 0. So we're making use of symmetry. Now we have to find the Z component. So Z center of mass, that'll be 1 over m triple integral dm times Z. So 1 over m. Now the dm is a triple integral right here. What is the dm? We can have the density, which would be mass over 2/3 pi radius cubed. And now we need a d volume in spherical polar coordinates. And then we would have the Z component, which would be, I'm just going to write Z right now, times Z. So yeah, let's go ahead and write this down. So we are looking for, this arrow goes to this here. Volume element in spherical polars. And yeah, you can use the standard spherical polar coordinates, so z would be the r cos theta, and your integration, your theta goes from, let's say, 0 less than or equal to theta less than or equal to pi over 2, and 0 less than or equal to phi less than or equal to 2 pi, and 0 less than or equal to r less than or equal to capital R. So those are the integration bounds. Oh, they're hidden right there. Oh well. With these boards. Okay, so that one I'd like to assign as well, but I'll get us started on it. I'll just remind us of the spherical polar coordinates. So when we're doing spherical polar coordinates, we have x, y, z. We have an angle theta here. Project down onto phi. And we have x equals r cos phi, r sine r sine theta cos phi, y is equal to r sine theta sine phi, and z is equal to r cos theta. So the r cos theta is what we're plugging in right here for the z. So we're doing a triple integral dr d theta d phi 0 to 2 pi, 0 to pi over 2, 0 to r. So we need the volume element. Or we need the rest of the volume element and the z that we have there as well. So r cos theta. Yeah, so let's go ahead and put that on the homework as well. That one's the homework. This one's also the homework. So we could find other things as well. Now, here's something I want to mention for the not too distant future. What if we had, instead of a hemisphere, half of an ellipsoid? Okay. So I'm going to put this here as a question. And this generally as well, what about integrating over ellipsoids? Because we're going to end up with a couple interesting examples of that. Or even if you're in 2 dimensions, integration over an ellipse as opposed to a circle. And for that, we're going to do coordinate transformations and a little bit of the general theory of integration will come into play as well. Yeah, so we'll flesh this out later on. But for the moment, we have a few good examples, and that's the one of our ingredients. Okay, so we now have checked off the center of mass. Okay, center of mass check. Okay, so what comes next with the center of mass is that next we have to talk a bit about the axis of rotation. This would be a good time to bring some demonstrations in. I'll bring them in next time probably. So the axis of rotation, when we have a fixed axis, it's not difficult to deal with. It's just any axis that we declare. So fixed axis. And just to demonstrate these things real quickly, I've got my book, and I could have an axis of rotation here. Use the pen. I could have an axis of rotation here, and the book would spin about that axis. Okay. I could have an axis of rotation down the middle of it, and turn it this way, and I could have an axis of rotation this way, turn it this way. Okay. So when we'll start with the fixed axis. So that axis cannot move. If I give this thing a toss, it can tumble around, and that makes things more complicated. But we're still in the fixed axis, so there's no problem there. Okay. So now we're going to get into some dynamical quantities. We have the center of mass. We're going to have the axis of rotation. So next what we want is kinetic energy of a rotating body. Kinetic energy of a rotating body. So let me make up a little more room here. Okay, kinetic energy of a rotating body. First of all, go back to our point formula, point mass, m sub I, v sub I squared. Now we're looking at, say, some body here, and there's our axis of rotation, rotating with angular velocity omega. With v sub I is equal to omega L sub I. And by L sub I mean the distance from the axis of rotation to the ith particle when measured, perpendicular from the axis of rotation. So there's the L sub I. Now, the kinetic energy is a half sum over m sub I, and this v sub I is now L sub I omega, the quantity squared. So this omega apparently characterizes the entire body, and we could pull it out. We'll end up with 1/2 sum over m sub I L sub I squared, put parentheses around there, times omega squared. This is the moment of inertia, the rotational inertia, or kinetic energy equals 1/2 I omega squared. Okay. So I've got the definition of the moment of inertia right here. And it has the dimensions mass times length squared. Of course, this is 1 over time squared. Dimensions are of course right. And so what we see is that this quantity depends on the mass distribution. The distribution of mass is very important. And this is rotational inertia. I'm going to put both of these terms down. Of course, that's called the moment of inertia. But it should just as well be referred to as rotational inertia because it's the resistance to the change of state of rotation. Best demonstration of this, we have a bunch backstage, I'll bring them in sometime, is if you rotate this ruler about the axis that goes right down the center. It's effortless. And all of the distances and the squared distances, in fact, this thing seems to have a couple centimeter cross section. So they're very small. Okay? So you've got all the same masses that comprise this ruler times the sum of all these very small lengths squared. On the other hand, if you just grab it here, everybody's encouraged to do this, by the way. If you have a meter stick, you grab it in the middle and spin it that way, you definitely feel the resistance to the twisting there. Rotational inertia, same mass that comprises the ruler, distributed out much further. If you make this the rotational of the axis of rotation, then you can really feel that difference, okay? And you've just got that much more length squared out there. So that the ruler is a good example. We're going to calculate that next. Okay, so rotational inertia, moment of inertia. Yeah. So let's also calculate some moments of inertia. And I'll do a couple here just to illustrate what I just showed you, and you guys, I'll give you a couple more to do on the homework as well. Okay. So, example. Moment of inertia for a uniform rod. So moment of inertia, uniform rod, mass M, length L. And the first one we're going to do, just like the ruler I have in my hand here, and we're considering these thickness dimensions negligible, and we're just going to rotate about the center of mass right there. So here we have, along an x-axis, we have L over 2. Here we have minus L over 2. And what do we have? We can easily convert that to an integration, so we'll say I is equal to the integral dm L squared. Okay. In this concrete case, we're going from minus L over 2 plus L over 2. The dm is going to be mass per length, because it's uniform, times dx, and the L squared is going to be x squared. Okay, so this is good. M over L, this is going to be x cubed over 3, evaluated from minus L over 2, L over 2, so we're going to have M divided by L. We have a third we have L over 2 cubed, and because it's from a plus to minus L over 2, we have another factor of 2 in there. Good, so what do we get here? M over L, we've got 1/3 L cubed over 8 times 2 equals, I'm going to cancel one of the L's, and 2 over 24, we're going to have 1/12 ml squared. ml squared. There's our moment of inertia. I want to give this second example a different name, but the idea is we're going to rotate about this end of the stick here. So that's our new axis of rotation, and we're integrating from 0 to L. So in that case, we're actually going to have the same thing. M over L x cubed over 3 from 0 to L. X cubed over 3, 0 to L. M over L times 3 L cubed equals 1/3 M L squared. So this is a great comparison. So we have the 1/3 compared to the 1/12. And you don't actually need a meter stick to do this. Even a 1-foot wood ruler will give you the feel for it. You just do it between your fingers like that. But yeah, you'll definitely feel the substantial difference. And just to go with physical examples, another step, if you really want to feel this, you put a ladder across your shoulders, you know, it's 10 feet in front of you and 10 feet in back of you, and then you try to turn, and you just feel that resistance to turning. Okay. So yeah, it's a subject that has a lot of interesting demonstrations. Good, so now we have the moment of inertia, and we're ready to talk about the dynamics of the rolling motion. We have the kinetic energy. So in fact, we could start setting up a little table here with the different quantities that you have in linear dynamics and rotational dynamics. Consult the clock here. Good. So linear versus rotational quantities. So I'll remind you of the x v equals dx dt, a equals dv dt. So I'll remind you that when you learned this in 4a, you had theta omega equals d theta dt, alpha equals d omega dt. So you could say the kinematics translates very nicely. So there's your kinematics. Now then, what did we have for dynamics though? We had momentum equals mv. We don't have anything for that yet. We had kinetic energy equals 1/2 mv squared. So the momentum I'm going to leave blank for the moment. Here the rotational kinetic energy is 1/2 pi omega squared. So we see we're substituting the mass for this mass distribution with I equals, we'll do it in the summation form. So what else is missing here? Of course, this could be the angular momentum. I omega. What's missing is the law, the dynamical law. So we could write m d squared x dt squared, or the two dots, is equal to f. And over here we're going to have to get the I d squared theta dt squared equals the torque. So I still have to get us the angular momentum and the torque. For fixed axis, actually this one is just as direct as the kinetic energy. The torque equation will do as follows. So moment of inertia times second derivative of the angle is equal to the torque. So let me derive that torque. So for this equation right here, for star, we're just going to consider K, and we'll call this the top view. We're going to consider a mass that is, we're going to do a profile, not a top view. Consider circular motion. Okay. So here's our axis of rotation, and we have a mass right here. Okay. And we're just going to write M change my mind. Top view. Top view after all. We got to see the torque. So we're doing a circular motion top view with respect to the origin. We've got a distance r here, and we have a force right here. So we have F times R, which is a torque. So we have tau equals F times R. On the other hand, we've got this dot here, this mass, accelerating linearly in that direction right there. Tau is F dot R, and we have M times the acceleration equal to F M times A times R is equal to F times R so M times R d omega dt times R is equal to F times R. So this is just how you can go through this as a point mass type of problem. And this d omega dt will be d squared theta dt. How did I write it down here? Well, I've got the distance step here. Let me get this way. We have m alpha r times r is equal to f times r. And this alpha is the d omega dt, or the d squared theta dt squared. So we have m r squared d squared theta dt squared is equal to f times r. So for a single point, for a single point mass, you've got moment of inertia, angular acceleration equals the torque expression right there. And if you integrate these up on both sides, then you will get this dynamical equation right here. Okay. So yeah, that's just the simple derivation of these. And you see this really nice set of analogies all the way down the line here. See how we're doing for time. Got a number of more things. Yeah, we're running out of time here. Okay. So yeah, this is just the rudimentary train of thought here. Okay. I wanted to add one more thing, and then we'll get to the applications next time. I want to get to the physical pendulum, but we're not there yet. Okay. So one note about moments of inertia. Moment of inertia and the parallel axis theorem. So we'll end with this today and start with this next time. The parallel axis theorem says if you have some body here, okay, there's the body, there's its axis of rotation, and this is going through the center of mass, okay, and now you rotate it around a parallel axis. I'll say it has a distance d. And this is a really useful theorem, by the way. Parallel axis theorem says that the moment of inertia I around this axis here is the total mass times d squared. So it's like it's point mass moment of inertia plus the moment of inertia around the center of mass. We'll get to the proof of that next time, or we could postpone it to the more general theory, but it's not difficult at all. What's happening physically is as you carry this thing, whatever this object is, as you carry it around, okay, it's rotating about this axis, and in one full rotation it's going around here, there's your md squared, but it's also rotating about itself, there's your center of mass. But this can be shown rigorously with no problem, and that goes, up under this discussion right here. And then we'll get some applications, things rolling down a hill, and I'll put here next, we're going to do, right, for this basic chapter, rolling motion, and more importantly, the physical pendulum. Those are our main goals for this fixed axis section, because that pretty much reviews the kind of stuff you did in Physics 4A. Okay, good. See you guys next time.